Welcome to Chapter 5 of my top-down networking design. This is designing a network topology. So I guess the first thing is, what's a topology? A branch of mathematical concerns with those properties of geometric configuration that are unaltered by elastic deformation such as stretching or twisting. A term is often used in computer networking field to describe the structure of a network. I hate that. That was a textbook definition. Topology is the overall physical or logical layout of a network, at least when we talk about topology in terms of a network. So, a random fact, if we are looking at topologists, a cup of coffee and a donut are considered the same shape according to their understanding of topology. So, design themes, normally a structure or hierarchy, redundancy, removing a single point of failure, modularity, scalability, well-defined ingress and egress points, as well as protection. This says protected perimeters, but on modern day network design, it's protection throughout, not just the perimeter. So first, why do we use a hierarchy model? Normally we do a hierarchy model to reduce the workload of the network devices. If it's done in such a way, we could help remove unnecessary broadcast domains. We actually can enhance simplicity and understanding of the network, as well as better facilitate changes. And the nice big thing is, with the hierarchy model, it scales good. Normally, in a Cisco environment, you learn the access layer, distribution layer, and core layer within a switching topology. If you're dealing with data center environments, there's a different structure, but for non-data center, this is a common structure. So the Cisco hierarchy design, normally the core is going to be fast, high-end routers, high-end switches. It's optimized for availability and speed. The distribution layer, that's going to have lower end routers and switches that implement policies and segment traffic. And lastly, the access layer switches, they connect users via switches to other devices. So there's a nice tree structure to this. So I said tree-like structure, but there are other types of hierarchy as well. There's a flat loop topology, which I don't really have seen that. We've typically see some type of hierarchy redundant topology. With multiple data centers, I have actually seen this type of deployment. If you're in a larger environment, maybe some type of mesh or full mesh topology, or partial mesh hierarchy design, where you have, again, the core, the distribution, and the access, and all of pretty much everything connected to everything else. This adds complexity to the network, but a good network architecture and a good network engineer is able to design this in such a way where this should not be an issue. What's really funny is if you put all of these routers and make them all switches, this could still apply. Core layer switching, distribution layer switching, switch or access layer switching. We have what's called a hub and a spoke. We may have a centralized area where everything handles back into. So the branch offices don't communicate with one another, they only communicate with HQ. That's a possibility. So we could avoid chains and backdoors. We can actually take this and we could reorganize it so that we have the appropriate types of connections. So how do you know when you have done a good design? Honestly, you can go and you can unplug something and nothing fails. A good redundant connection plan, whether it's switching environment, routing environment, whatever. If you unplug something by accident and the network still is survivable, you know you've done a good job. You also know you've done a good job when you can scale with it. You add in another branch office or another building and you don't have to redesign everything. Or you may be doing some troubleshooting, and the troubleshooting actually is very simplified based off of your design. You can also go to your network documentation and you pull it out, and it's the same as your actual network. That's huge, because again, it's very common for network architectures that design a network and then for them to go on to another project. And then the network managers maybe then add or remove or manipulate or change the network without updating any of the documentation. So that's always a nice, lovely concern. Cisco has a safe security reference architecture. Again, that's dealing with core, the management, it's dealing with everything. The nice thing is Cisco design principles, like when you've done a CCDA or CCDP, you get to learn about a lot of the more design specific options. I currently hold both a CCDA and a CCDP. I am a design professional. I have been working on my DE exam so I can become a design expert. But the more you get into the design, the more you need to start realizing the importance of, well, routing and switching and all of the other major areas, because again, they all interconnect, especially when you're doing design. So campus topology design is normally a hierarchy. It also is very modular because again, as you add in additional campuses, different buildings, different locations, you need to be able to maximize how quickly or how efficiently you can add those new nodes to the network. Normally, we could be minimizing the size of bandwidth domains, minimizing the size of broadcast domains, provide redundancies, whether that's in the form of mirrored servers, whether that's in the form of multiple links or multiple pathways, many ways to take that. A simple campus redundant design could be that we have two switches and every PC gets two connections. So realistically, that's not going to happen. Probably you're going to end up with access layer switches with one link to our hosts, but you limit how many access switches control vast majority of the rooms. For example, in my current design, we have an access layer switch, one per classroom. Happens to be their classes are under 24 nodes, so kind of does help out. But that way, if that one classroom loses internet, we know, hey, it's probably an access layer switch issue, as opposed to, hey, everything on the third floor is lost access. Then that goes, oh, maybe that's a distribution switch issue. The nice thing is, no one really pointed out loops yet, but we have a mechanism called Spanning Tree Protocol, STP, and this is put into place to kind of help logically prevent loops. Very simple to implement. I've done numerous videos on STP. I've done some long videos on STP, well, MSTP, but when we have a looping environment and a broadcast occurs, we actually end up with a broadcast storm, and that's where both switches keep broadcasting the storm over and over and over, and it's consuming more and more resources. The nice thing is with STP, it can logically shut down a interface. That way, there is no loop. But if another link goes down, the one that was shut down because of the loop has the ability to come back up, as opposed to when you physically have the loop cut off. I've had it where we've had redundant switches, but the network administrator at the time actually preferred to have everything physically unplugged, not using STP. Some network engineers are like that. It is what it is. Bridging or switchings that are running STP, again, they actually elect some type of root bridge, and then that root bridge actually controls what ports are going to be turned on and turned off. Normally, the root bridge has ports that are going to be called designated ports. And additional switches will have root ports. So let's go into that. Here we have a root bridge, happens to be switch A. We have port 1 and port 2. Well, why did bridge A become the root bridge? Happens to be they have the lowest bridge ID or the lowest MAC address, if there's a tie. You'll notice that we have several ports. So, what port do we want to turn off to stop our loop? We actually might here turn off port 1. Even though both are 100 megabit connections, we may actually disable the loops or the ports that turn off loops. An interesting thing actually here is the port that is facing or going towards the root bridge is called a root port. That means traffic will go to the root port to get to the root switch, as opposed to designated ports. Designated ports are the ones going away from the root bridge. But you're going to notice, why is this guy a designated port? Because if we have switches beneath here, this is on the way away from it. So we can also start pruning ports. Happens to be here, we turned off this port here to prevent our switching loop. We could have turned off one of these ports up here or one of these ports, but the selection process controlled by our root bridge elected to turn off that port. So what ends up happening is that port becomes to a blocking port. Everything else becomes still being able to forward traffic. That way, traffic can flow normally. Why does this one become disabled? In this scenario, this one actually is blocking. So this one actually gets disabled because there is no endpoint to it. So scaling spanning tree protocol keeps the switch network small. They use a BPDU to help detection on Cisco switches. Few of the STP are part of the IEEE 802.1W. There are a few different types of spanning tree. One of them is rapid spanning tree protocol, as well as some other spanning tree protocols that are out there. Again, I've already prepared videos on spanning tree. Go ahead and watch those. We also have virtual LANs. That's always a big one. Virtual LANs actually allows for a set of devices that belong to a specific sphere of control to be grouped on physical switches. So in this example, we have two different switches, switch A and switch B. All stations for A connect to switch A. All stations for B connect to switch B. But we have to have two switches. Here, we could actually have one switch and actually map it so that these happen to be for VLAN A and these happen to be for VLAN B, and they're programmed per port. So they're all are part of VLAN B's port. These are all part of VLAN A's port, and they will act as logically two separated switches. We can span that between, again, multiple switches. This in between is called a trunk. It will actually act as a bridge between. So this will carry both VLAN B and VLAN A's traffic back and forth. The important part here is VLAN A will not be allowed to talk to VLAN B unless you have a layer 3 device. Again, the network layer deals with interconnections. or inter-network communications, meaning if they're on different networks, you have to have a layer 3 device. If they're on the same network, they can communicate because they will actually communicate on the same network using MAC addresses, as opposed to different networks have to use IP addresses. And again, routers handle IP addresses, but there are some layer 3 switches that can also handle IP addresses. We have our wireless LANs versus VLANs. A wireless LAN is a different VLAN, but typically is for wireless. That way we can have a wireless network and a wired network, and they're two separate networks. Wireless LANs do facilitate roaming, meaning you can be mobile. Workstation-to-Router Communication. Normally we could do things called ARP or proxy ARP. That's not really a good idea. Normally our routers on our LAN side will act as our default gateway. That way things that are going to leave our network we can just forward to our router. Normally ICMP, router solicitation, which is not so widely used, but I've seen it used a lot, allows for, again, solicitation using ICMP. ICMP is ping. We also have the default gateway protocol, which normally is provided by DHCP. Sorry, it's a default gateway, not a default gateway protocol. The default gateway is, again, our router, and basically it's our egress point. If it's not on the network, where do I send it? We can send it to our default gateway. But if we only have one router, one exit point, one egress point, what happens if that goes down? We actually have the ability to do some type of first hop redundancy. And one of the first things there is something called Hot Standby Routing Protocol, or HSRP, which is used for redundancy. This is just one type of first hop redundancy connections, but HSRP actually gives us a virtual router, where we have two physical routers that are up with a similar configuration, and they both own the virtual router, but only the active one processes it. So when you send it to the default gateway, it will actually be to that virtual router. That virtual router will send it to the network. The active router controls the virtual router, but if the active router goes down, the virtual router gets taken over by the standby router. That way, that virtual router is always available. We have multi-homing for internets. That's basically where we can have multiple paths out to the internets. We could have one ISP with two connections. We could have one ISP with two branch offices connecting to the ISPs. Because if you're here, where is my... Nope, didn't want that. If you're here, that way goes to the internet, but so does that way. So which way would we go to the internet? We could have multiple ISPs, ISP1 and ISP2, and again, multi-homed ISPs 1 and 2 as well. We have the ability to do some type of DMZ or demilitarized zone. So we may end up with a firewall. All right, it is not being nice today. We can end up with some type of firewall here. So as traffic goes in from the internet, we may block certain traffic. Anything in the DMZ we may allow ports open for. And then we had another firewall here to protect our enterprise network. That way, things like mail or email or web servers can be in this DMZ zone. That way, traffic from the internet does not have to go to the enterprise network, then to the servers. They will be already between both our firewalls. Here's exactly what I just pointed out, but a slightly different way. So we'll have a router, we'll have a firewall, but you notice all of these are behind the router. Maybe we add another firewall up here and add the DMZ up there, and then another firewall to protect the enterprise network. That's again, just suggestions. Normally the DMZ is off by itself and the rest of the enterprise network is off by itself, both protected by a firewall. That's actually the end of this chapter. I want to leave you with some review questions. Why are hierarchy and modularity important for network design? What are the 3 layers of the Cisco hierarchical network design? You should know that it never goes away. What are the major components of a Cisco enterprise composite network model? And last one, what are the advantages and disadvantages of the various options for multi-homing and internet connections? That's actually it for this chapter. I want to thank you. Welcome to my review of Chapter 7 of the Top-Down Network Design textbook. In this chapter, we're looking at selecting switching and routing protocols. So this is always really good, though I don't quite think this small of a chapter could really go that in depth with writing protocols or switching protocols, but we're going to see. So switching and routing choices. For switching, at least if we're looking at layer 2 switching, it's a transparent bridge switching. We have multi-layer switches, layers 2 and layer 3. We have some techniques that we could put in place, things such as STP or spanning tree protocol, or the variations of spanning tree protocol, as well as some VLAN type technology. What's really funny is, I guess you can call those choices, but I mean, those are just basic features that are in a enterprise class switch. Routing, we can have a static or dynamic routing. You can have your own static routes that you, the network admin, happens to design. Normally, if we're talking dynamic routing, we're talking normally a distance vector or link state. Those are 2. There are some hybrids. Interior or exterior gateway. A great example is like BGP. There is a interior gateway BGP called IBGP, and there is an exterior gateway protocol for BGP called eBGP. BGP is typically the routing protocol that the internet uses, so you can actually implement BGP on smaller networks, but there's some complexity to that. I'm actually going to not touch too much on that. If you want to know more about BGP, review my videos on BGP. Going forth, we have to understand how we're going to select the appropriate protocols. Normally, we'd be looking at things like budget, traffic characteristics, resource utilization, resource being bandwidth, but the switches and the routers both have finite resources. They both have limited memory and limited processing power. Actually, this is kind of important because I just realized this the other day. I have a Sonic wall, which is owned by Dell, and I pay for a 200 megabit connection at my house. And my Sonic wall TZ215, when I do a speed test, it gets to about 145, 150 megabits per second, and then stops. And I'm like, okay, that's kind of weird. Maybe my cable provider is not giving me the appropriate bandwidth. So first we called them and, we verified. And turns out it actually was my router. And it had never dawned on me to check CPU usage. Turns out when I did a speed test, at about 145 megs, the controlling plane and memory for my Sonic wall were at 100%. So the Sonic wall device could not process more traffic. It was as fast as it could go. Even though on that particular model, I had gigabit in and gigabit out, it didn't mean that the processor that was in the device was capable of handling the traffic going through it. So that was kind of interesting. Other characteristics could be the number of peers, the number of technologies, uh, what type of technology we're going to be working with. Are we working with VPNs? Are we working with site to site? Are we working with mobile clients? There's a lot of things that are there. One of the big things is capability, scalability, and adaptability. If I get a particular design and I want to be able to quickly change or add things to it, can my protocols keep up with that? For example, if we're doing everything statically, trying to make quick changes, static is not going to work. So the capabilities of scalability have to be there. One of the last big things is this whole support for authentication. I'm sorry, I disagree with that. There needs to be full-fledged security support, not just authentication. We're talking at least AAA. Authentication, authorization, accountability. We need to be able to see what's happening, who's doing it, or who's not supposed to be doing it, all of that good stuff. We need to be able to verify the routing protocols have the appropriate authentication factors, that we're only partnering or peering with our adjacent neighbors that we approve of. No, well, not really no. We should have a mechanism in place so that we only accept maybe route changes from known devices or known paths so that we will have no poison routing or poison switching or poisoning of our MAC tables. Sorry, I just did a video on ethical hacking where we were doing art poisoning. So, yeah. So we have to make a few decisions. We have to keep goals, the mission statement, budget kind of in mind. We have to understand the technologies that we're working with. For example, if we're doing all Juniper, can we do EIGRP? Well, no. EIGRP is Cisco proprietary. So we have to keep in mind what are we going to be doing. We have to have some change management plans, some contingency plans, some type of decision table is always really good. That way we can discuss what is the appropriate protocol. So IGRP, well, this is what's really weird. I've seen IGRP displayed as the lesser of the IGRP, but I've also seen IGRP as interior gateway routing protocols, more as a generic name for interior protocols or routing protocols. So I've also seen it as IRP. So I just want to put that out there. So BGP, OSPF, EIGRP, those are going to be some common routing protocols. Normally BGP not so much, unless you have a large network. OSPF and EIGRP are pretty common. So let's get back into our switching. So the nice thing here is, what's the purpose of a switch? Forwarding frames, normally transparently. They need to learn the appropriate MAC addresses coming on which ports so they can build a MAC address table, also called I always forget the appropriate, I always forget, I keep wanting to call it CAN, C-A-N, but it's really CAM, C-A-M. Basically, we're looking at the forwarding information base, the FIB, which is also known as the forwarding table, and CAM table. It is the most commonly used in network bridging and routing, and similar functions to a popular interface. It's very similar to a dynamic table that maps MAC addresses to ports. So MAC address table is just one of them. Also, when we're dealing with switching, we have to talk about security and proper resource management so that we're not getting floods of frames. For example, unicast addresses that haven't been learned, or broadcast addresses where we have bridging loops. We should have filters in place so we can filter frames from going out the incorrect ports. We also have to be careful with flooding broadcasts and flooding multicasts. Again, a big part of this goes back to proper design, proper layout of our switches and our switch network. That way we can put certain features into place that help to help prevent broadcast flooding. There's lots of features that are built into switches that people don't realize that are there, like stateful frame inspection, or SPI, or STP, or variation versions of STP. Switches are pretty powerful as long as you understand the technology that they're using. A switching table on a bridge could be as simple as this: MAC address tied to what port. Cisco spanning tree, or again STP. There's several versions. There's port fast and uplink fast and backbone fast. You can actually have unidirectional or loop guards. Again, there are so many different types when it comes to spanning tree. Spanning tree is fairly simple until you get into like the MSTP, or the multi-state spanning tree protocols. Those get pretty complex, but again, not super hard. Again, the whole redundant link for scalability is important, but at the same time, also understanding how we do our STP. That's also extremely important because you can actually start blocking connections or turning off links with STP if you're not laying out your network correctly. Normally people turn STP on if they even turn it on, and then they walk away. But you kind of have to understand how STP works so that you don't start disabling links that are important. So be careful when it comes to STP. Don't just turn it on and walk away. Make sure you understand what links are going down and understand why. Other things when we're dealing with protocols for switching, we're talking ISL, or inner switch links. Normally they're going to be tagged. In a non-Cisco switch, they normally don't call them VLANs, they call them tagging. And basically you have to tag the item coming in on that port, what VLAN you are. I was programming a Netgear switch, and we set it up at the appropriate 4 VLANs that we needed. VLANs 4, 5, 6, and 7. But the interesting thing was, on the Cisco switch, we called it VLAN 7. On the Netgear switch, we actually had to create VLAN 7, but we had to tag that port, so any frame coming in on that port would be tagged VLAN 7. We have a few other types of protocols. We have the IEEE 802.1q, which is a tagging protocol, which is non-Cisco proprietary. 802.1q is a pretty common one. Normally when I teach switching and or like CCNP level switching courses, I'm teaching 802.1q. We have trunking protocols for VLANs called VTP. VTP is always really good, always very dangerous, but always really good. Helps the network a lot more than people realize if implemented correctly. Moving on is our routing protocols. This is always real fun because you have to understand several things when picking out the appropriate routing protocol. They all have the same general goal, which is to share network reachability among all the routers. So that's one thing. But how efficiently do they do that is, well, different. Also, how do they do that? Again, it's going to be different. They differ in ways interior versus exterior. The metrics. How do we choose the appropriate path? That's going to be the measurements. It's metrics. Dynamic versus static versus default. Distance vector versus link state. Those are big ones. Classful versus classless. How scalable they are. All right, so realistically right now, classful probably is not even in consideration anymore. Most routing protocols, most networks that we're using nowadays are classless, hands down. So then becomes how big of a network, how small of a network, And that kind of can help start narrowing it down the appropriate protocol based off of that. So let's look at interior versus exterior routing protocols. Interior routing protocols are used within an autonomous system number, the same sphere of control, where exterior routing protocols are used between autonomous system numbers. BGP, great example. BGP uses autonomous system numbers. So the next common question is, what is an autonomous system number? General two definitions is a set of routers that present a common routing policy to the inner network, or a network or set of networks that are under the administrative control of a single entity. That's why I say sphere of control. For example, Cox, they control all of the routers in their network. That's probably one sphere of control. Comcast, they probably have, again, their own autonomous system number. They are not the same as Cox. Comcast and Cox, they're similar, but they're different. So they actually have probably different autonomous system numbers. So routing protocol metrics, different ways to look at how to measure. For example, bandwidth or the capacity could be reliability of the line, the delay, the load, the hop count, the costs. All of these things could be different metrics depending on the routing protocol. So which is the best path? It depends. How are we measuring? So that's where it gets a little bit more complex. So sometimes routing algorithms could be a static route, which is normally calculated beforehand. It's manually programmed. We could have a default route. If I don't know where to send something, automatically send it here. We could have Cisco's on-demand routing for a stub network using a CDP. That's I don't have much experience with, but most of my experience has gone with dynamic routing protocols, distance vector or link state, or static routes, depending on again how big the network is. Static routing examples, here would actually have to say, if you want to go to this network or this network, send out this interface. Here we have IP route. If you want to, it should be source to destination. So we're looking at router A. Let me grab my pen real quick. If we want to go here with that subnet, send here. They know what's directly attached. Like router A knows about this. Router C knows about this. Router B knows about this. You only know what you're directly connected to. So here it's essentially saying if we want to connect to 1 and 2, 1650, if we want to go to that network, which is this network right here, send here. It happens to be this IP address. So basically, we're going to forward the information, I hate using so much red, to router B. A default route would be send everything out to this interface. So any IP with any subnet send to this IP address here. Which, I mean, does work, but what is router B supposed to do with it? What if you're trying to get to 172.1650.2? Does router B know about it? So that's one of the problems. We have to be a little bit more specific. So let's talk about distance vector. Routers maintain a routable table that lists known networks, their direction, also known as their vector, to each network, and the distance or the hop count to each network. Routers periodically, typically every 30 seconds, will transmit the routing table via a broadcast packet that reaches all other routers. Once all routers have all information, it's called convergence. But what happens if the network doesn't change? Is it gonna keep sending the router updates even if no changes have occurred? That's an issue with distance vector. Router updates the routing table if necessary based on received broadcasts. If it doesn't receive an update information, it just receives the original information or old information, it still has to process that packet. So it's a waste of resources. Distance vector routing tables, again, distance could be hop and where to send it. For example, if we're looking at the routing table for router A, 172.16.0.0 is the network. It has a distance of 0 because it knows that's a local network. It also realizes that it's going to go out port 1. If we want to go to 192.168.2.0 as the network, we're going to send it to router B. Normally it's not quite send to router B, it's going to be send to the appropriate IP address for it, but that was just more of a so that you can understand it. Link state routing protocols normally deal with sending updates only when there is a change. That way we don't have to waste resources. Routers that detect changes create a link state advertisement or LSA and sends it to its neighbors. That way, again, once everyone knows about all changes, it's converged. The neighbors propagate the change to their neighbors and so forth and so forth. The routers update their topological database if necessary. But again, this is when a change occurs, not every 30 seconds. So distance vector algorithms keeps a list of networks with next hop and distance metric. Link state algorithms keep a database of routers and links between them. The link state algorithm thinks of the inner network as a graph instead of a list. That's a big thing. When changes occur, link state algorithm applies, I can't even pronounce that, shortest path algorithm to find the shortest path between different nodes. Again, link state, the big thing here is it looks at it as a graph and updates when changes occur. Distance vector looks at it more like a list, uses next hop and distance as metrics, and updates every 30 seconds. So, how do you know when to choose which one? Distance vectors, you might choose it when you're choosing more of a simple or a flat topology, or maybe a hub and spoke, or if you're not really a network engineer and you're not quite familiar with how these work. But convergence time is not really that big of an issue. Link state is again a hierarchical normally used by more senior administrators, and that's when fast convergence is critical. I'm not going to argue with this slide. Both have their places. What you normally want to do is look at the characteristics of the metrics that are being used and your network and choose the appropriate routing protocol based off the metric that fits your network. Dynamic IP routing protocols, distance vector, things are going to be like RIP or EIGRP or maybe even BGP. Link state is going to be the common OSPF or IS. Again, normally we're looking at EIGRP versus OSPF and sometimes BGP. BGP is a hybrid distance vector, but we're not going to get too much into that. Looking at RIP, RIP is a standalone routing dynamic routing protocol that's really easy to configure and really easy to troubleshoot, but it's kind of crappy. I mean, if you have nothing else, RIP works, but it's classful It doesn't really like classless networks, and the functionality is just not really there. RIP version 2 does support prefix routing and finally supported VLSM. It includes simple authentication, but that's about it. IGRP solved problems with RIP, like the whole 15 hop limitation. RIP also has that 30-second update timer, where IGRPs could use 90. EIGRP is an enhanced IGRP. It adjusts to the changes in the network quicker, or very quickly. It has incremental updates, certainly are containing only changes. That way you don't have to do the entire routing table. It does update more reliably. It also updates and delivers more reliability, or more reliable, not reliability, sorry. Routers keep track of neighbor routing tables and use them as feasible successors. You learn a lot about feasible successors when you go for your CCNP route course. That's a huge topic. Same metric as IGRPs, but more granularity. You end up with a 32-bit instead of the traditional 24-bit for metrics for that. OSPF, or Open Shortest Path First. It adjusts the changes quickly, supports very large networks, does not use a lot of bandwidth, and does have authentication. OSPF is very common, so is EIGRP. Normally, OSPF metric is a single dimensionless value called cost. A network admin assigns an OSPF cost to each of the routers, and that way you can then start manipulating the cost based off of things like bandwidth. On a Cisco router, the cost of an interface defaults to 100 million, divided by the bandwidth of that interface. For example, a 100 megabit connection would have an interface cost of 1. There's actually a interface cost breakdown for OSPF metrics, which we may or may not be looking at here shortly. OSPF does connect via area border routers, or ABRs. All areas go back to area 0. Area 0 is classified as their backbone. And we have ABRs that connect the different areas back to 0. All areas connect back to 0, period. Is a link state routing protocol designed by ISO, but I think I've seen this once, and that was it. BGP allows routers and different autonomous systems to exchange routing information. That's probably because we're going to be looking at exterior BGP or BGP. It's used on the internet and large companies. Does support router aggregation. Its main metric is the length of the list of autonomous system numbers, but BGP also supports routing based on policy. So that's actually a nice brief overview of basic switching and basic routing for now. I'm going to leave you with some review questions. What are some of the options for enhancing spanning tree protocol? What is spanning tree protocol? What factors will help you decide whether distance vector or link state routing is the best for your design? What factors will help you select a specific routing protocol? And why do static and default routers still play a role in many modern network designs? That's it for this chapter. I want to thank you. Okay, so I wanted to discuss some follow-up items. One of the first things is our APA formatting and citation. That goes for both our IPs and our discussions. Remember that we have to do all of our work according to the APA manual. So if you're not sure how to do that, go online. You can type in APA formatting. If you don't want to look it up online, you can go to any of the tutorial services. We have a writing, we have a library service. They can give you additional resources on how to do APA formatting. That's important. That's not going away. In discussions, same thing. We have to be doing our citations in our discussions, because one of the big things is, for our citations, we're building off of other people's works. So it's a way for us to verify what we're claiming is supported by the literature. So when I say something at the sky is blue, you can take my word for it, or if I provide a citation, you can take an expert's word for it, and then I built off of that. So it just kind of increases your credibility. We should be at least citing in every post, or as much as possible, because again, we're trying to link what we've done back to the literature. Same thing in our IPs. Every paragraph should be tied to a source. Every paragraph is an idea, and every idea we need to have support within the literature. And I know at this level it's not that big of an issue, but you want to get in the habit of doing that, so when you start doing higher level work, it's second nature. Also, length. We don't need posts that are great job. I mean, don't get me wrong, it does add to it, but when I start grading for posts, I'm not doing full credit for those that have 3 posts and 2 of them are great jobs. I don't count the great jobs as a post. For our discussion board, I'm looking for 3 solid responses with citations. For our papers, I'm looking for 3 pages of content with citations. So what I mean by content is, that's 3 papers on topic. That's not a cover page, that's not your reference page, that's 3 content pages. 2 if you're really good, but I'm really looking for 3 if you're doing diagrams. Diagrams totally are okay, as long as you're doing them within APA formatting. Lastly, grading. Again, I grade heavily off of attempt, like if you're putting an effort into it. Like if you did 2 pages and you did a few citations, and I could see that you were making an effort, I'll meet you. But if you post once, or you did a page and a half with 1 citation, you know, that really isn't you making an effort. If you get stuck, don't get me wrong, some people a page is a lot. If you get stuck, you have plenty of resources to bolster up your paper. You can contact me, I'll help you. If you don't want to contact me, we have a writing center, we have a tutorial center, we have plenty of help for you to get. If you need tutoring, there's a lot of tutoring out there. And again, provided from the school. All you have to do is say something. For our tutorial lab, we have tutorial services for SQL, we have tutorial services for database, we have tutorial services for math, English, writing, research, library services. I mean, we have a great amount of tutorial services. And if we don't offer tutoring in a specific area, you can ask for it specifically, and they will find tutors for you. So you could not get tutoring, because you can. If you ask for help, the school will get it. If you cannot get it from the school, there's other help. I will sit down with you. I will do as much as I can with you if you need one-on-one. If you need tutoring and you don't get tutoring, that's not a failure on my part. That's not a failure on the school's part. That's only a failure on your part, because there's plenty of opportunities there. You have my number, you have my email, you have 2 emails from me, you have my cell phone number, you have plenty of ways to get a hold of me if you need help. And again, if you don't capitalize on help and you need help, that's on you. Because there's plenty of help out there. All you have to do is say something. Thank you.